Welcome to this explainer. Today we're diving into what's arguably the most powerful symbol of national sovereignty ever built. I mean, we're talking about a structure so unimaginably vast, it literally acts as 4.5 acres of floating territory. It can project a small city's worth of personnel to any ocean on the planet. But, we aren't just going to look at the sheer awe-inspiring size of the new Gerald R. Ford-class aircraft carrier. We're actually going to decode the staggering physics that make it tick. Because if you ask an engineer, a modern carrier isn't just a ship. It's a massive, high-stakes optimization problem floating in the middle of the sea.
So let's dive right into this massive puzzle. How do you actually go about designing a steel structure that weighs a mind-boggling 100,000 tons, yet somehow keep it agile enough to hurl a 30-ton jet into the sky every 45 seconds? It's crazy to think about, right? You have to manage the power draw of a medium-sized city, all while keeping an ear out for an invisible armada of submarines lurking right below the waves. It's this ultimate high-stakes balancing act of extreme forces, material science, and global logistics. To really grasp the scale of those forces, just think about this: 0 to 250 kilometers per hour in under 2 seconds. Yeah, that's the violent, completely adrenaline-pumping reality of the launch deck. You've got a stationary fighter jet just sitting there, and in the literal blink of an eye, it has to be accelerated to flight speed. The immense energy you need to conquer that inertia and safely throw an aircraft into the sky is honestly almost hard to wrap your head around.
Okay, Section 1. Launching jets with magnets and the major shift from legacy steam to smart tracks.
For over 50 years, the undisputed gold standard for getting jets airborne was steam. But there's a huge contrast between that older tech and today's new smart systems. See, the old steam setup was essentially a dumb system. When you fired a steam catapult, it acted like a literal hammer blow, hitting the aircraft with maximum force right out of the gate. That puts immense shear stress on the airframe. And sure, that's fine for a heavy F-14 Tomcat, but if you try that with a lightweight modern drone, that violent hit could literally rip the front landing gear right off. No way around it. So enter EMALS, the Electromagnetic Aircraft Launch System. It actually uses the exact same physics as Japan's Maglev trains, sending electric current through thousands of copper coils to create this moving magnetic field. And the best part? It's smart. Sensors are constantly monitoring the jet 40 times a second, tweaking the magnetic force to give it a perfectly smooth acceleration curve.
But that smart acceleration brings us to a really massive logistical hurdle. Accelerating a jet with EMALS requires a peak power draw of nearly 500 megawatts. To put that into perspective for you, pulling 500 megawatts instantly is enough to completely blow the electrical grid of a small city. If you tried to pull that kind of juice directly from the ship's nuclear reactor the exact second the pilot salutes, you'd trigger a catastrophic systemic issue. You would literally black out the entire ship just to launch a single jet. The engineering workaround for this problem, though, is absolutely brilliant. Instead of relying on a direct draw from the reactor or using chemical batteries, the Ford class utilizes what's called intermediate energy storage. Think of it like a massive mechanical battery system. It uses sheer physical mass to corral the required energy, holding it in reserve until the exact moment it's needed, and then safely discharging all of it into the catapult in just a matter of seconds.
So here is the crucial point about how they actually store that energy. They use 4 gigantic rotors, each weighing 12 tons, to act as flywheels. Between launches, these colossal masses of steel are spun up to a mind-boggling 6,400 revolutions per minute. I mean, just imagine spinning 12 tons of solid steel at that speed without tearing the ship apart. It's a total triumph of applied physics. It lets them store immense kinetic energy locally, bypassing the reactor's immediate limits and completely providing a ship-wide blackout.
Moving on to Section 2. The art of controlled crashing, or how to stop a 20-ton jet in just 100 meters.
If launching a jet is this violent explosion of outward energy, recovering one is the exact opposite challenge. Catching an incoming jet traveling at 240 kilometers per hour and forcing it to a dead stop in just 100 meters is what pilots literally call a controlled crash. And safely managing those extreme forces, that is an absolute masterclass in fluid dynamics. See, older solid cable systems used to suffer from catastrophic failures because of something called hydrogen embrittlement. To avoid that completely, the modern advanced arresting gear changes the game. When the tailhook snags the wire, the cable pulls on a drum. But here's the trick. That drum spins inside a water-filled chamber. By using fluid resistance to brake the jet, the water smoothly and progressively absorbs all that kinetic energy. It's actually the exact same logic used in the hydrogas suspensions of heavy tanks. using fluid dynamics to elegantly dampen otherwise highly destructive forces.
Now for Section 3, F1 pit stops at sea and optimizing flight deck logistics.
Beyond all those brutal mechanical forces of takeoffs and landings, there's a completely different kind of engineering happening right on the surface. The flight deck itself is just a masterpiece of spatial optimization, specifically designed to keep up the relentless pace you'd need in a high-tempo conflict. On the older Nimitz-class carriers, the command tower, or the island, was situated right in the middle, which created a massive logistical bottleneck. But by simply shrinking that island and moving it further aft, engineers completely transform the flow of traffic. The result is a massive 33% increase in the deck sortie rate. This layout basically lets engineers treat the deck exactly like an F1 pit crew would. Jets can land, rearm, and refuel along these highly optimized paths without ever crossing the path of another jet getting ready to launch. And honestly, those saved minutes, they're the razor-thin difference between maintaining air superiority and being overwhelmed.
Which brings us to Section 4, the nuclear heartbeat, located 30 meters below the waterline.
To truly understand how all these high-tech systems, from the smart catapults to the complex radar, stay alive, we have to plunge 30 meters below the waterline. Down here is the colossal power source that makes this entire floating airport possible, the twin A1B nuclear reactors. And guys, these aren't your standard portable units. They're meticulously engineered to operate for a staggering 25 years without ever needing to be refueled. Even more impressive, they produce 3 times the electrical power of previous designs. They provide the massive electrical heartbeat required to sustain the EMALS launch system today and ensure the ship has the excess power grid to support future hard tech, like high-energy lasers for fleet defense, tomorrow.
So where does a lot of that excess power go right now? Well, situational awareness. Modern carriers are up against some incredibly advanced threats out there, including what's known as a great underwater wall of stealthy titanium submarines and acoustic sensors. To counter this, the ship runs dual-band radar. This system is so hypersensitive, it can track a bird-sized object from hundreds of miles away. But running a radar with that kind of fidelity requires the electrical equivalent of powering 10,000 homes. Without those next-gen reactors, doing that would just be impossible.
When you step back and really look at the whole picture, the modern aircraft carrier truly is the golden intersection of engineering. Every single inch of this vessel is a testament to pushing material science to its absolute limits. From the highly resilient Inconel alloys protecting those nuclear reactors, all the way to the advanced carbon fiber composites making up the jets on the deck, it's a total masterwork of manipulating materials to ensure the mission succeeds against the unforgiving laws of physics.
But building a machine this complex is a massive $13 billion gamble per ship. And it leaves us with a pretty provocative thought. As incredible as this engineering is, can this ultimate critical system really maintain its dominance? With modern threats like hypersonic missiles appearing on the horizon, giving you minimal time to intercept, the carrier's continued survival is going to depend entirely on how far we can push these exact systems.
If looking at how a massive ship balances extreme forces gave you a dopamine rush today and you want to truly understand the system logic behind it all, well, the interactive lessons at Brilliant are exactly what you need. Brilliant helps you master the very concepts we talked about, like the fluid dynamics behind the water twister arresting gear, or the classical mechanics that keep a 100,000-ton hull completely stable while jets are literally hammered off its deck. Instead of just memorizing boring formulas, their hands-on lessons actually build your intuition. You can start with scientific thinking or jump right into applied physics. So, if you want to level up your own engineering toolkit, head over to brilliant.org/systemlogic to check it out. Thank you so much for joining me for this explainer. Keep your curiosity sharp, and I'll see you in the next one.